are cases where recursion is actually the best way to do something. And this is one of those cases. Okay? When we want to make sense of a list, now this is a relatively simple list. It might feel complicated, but relatively simple. The blue is the top level list. The green would be the second level down, and the red would be the third level down. So if I break that list up into a tree structure, it's going to look like this. So I have the main list. Now, if you can imagine a data structure that's like this, but number one, it's way bigger and way more complicated with way more levels. And especially, here's the big one. If we don't know how many levels there are, in other words, we know that there are 3 levels here. But if I had a list where I said, this list has 1,000,000 plus names on it, and I don't know how many levels deep it goes, but I would like you to write me a piece of software that can figure that out. That is a case for recursion, because what recursion can do is keep digging until it hits the bottom, and then it comes back out. And it can do that multiple times as it traverses this list. So how does that work? How does recursion do this? If I take that list, and you can recognize that this is the same list with the same structure, if I take a recursive function and I tell it that we're going to count how many names there are total in all of these lists, but I don't know how deep this goes, and I don't know how many names there are, but I just need you to follow your nose and cover every single one. This is the path that the recursive function would take, okay? So basically what it's saying is, every time I find a list, I'm going to explore that list. So the first name, it says, okay, there's a name. I'm just going to count it. That's 1. Second spot over here, index 1, in that first top level list is a list. It says, oh, I found a list. Now this is where a recursion level occurs. And it goes into, it calls that function using that list. And it says, okay, well, the first one's a name. Count that. That's 2. Oh, I found another list. I'm just going to go explore that list. And when it gets to the end of a list, it goes right back up to where it left off before. That was when I said the finishing part. So it's coming back out, finishes that list, comes back up, keeps going. Oh, I found another list. And it just keeps doing that. And you can see it doesn't matter what the structure is or how many lists or how many levels. It does not matter. This algorithm or approach to problem solving will figure it out. So let's take a look at that code. This recursive list counter, I've got a function called count strings. And its job is to count how many names there are. And I'm going to start it out by giving it a list. And I'm going to start it out as level 0. And it will go through and it'll say for each item in the list, this is code that we're familiar with, it's not new. For each item in the list, if this is a list, then we are going to say, I found a list. And then look what it does next. It says count plus equals, what's this right here? Count strings. It's going to call itself. So it's literally right here in the middle of this function going to start another instance of this. And it's going to go back up and it's going to say, okay, let's start counting at 0 here. And we're going to process that list and it's going to say for each item in that list. And it's just going to keep going until it hits the end of this list, and then it's going to start rolling things up. Now what I've done, you can see I've put all these print statements in here. This is really not that much code if you take out all of the print statements. It's a relatively small amount of code. But what I want to show you is how this traverses that list, because it's kind of interesting. But that's the whole function there. And you can see almost like a third of the lines in that function are just my print statements that tell us what's going on. Okay, so we're going to start at level 1, and we're going to give it this list up at the top. And we're going to run that. Goes through awfully fast, of course. But look at let's take a look at this. So we've got this list, right? We've got processing level 1. Okay, so it's at the top level. It says counting atom. Now level 1 has 1. Then at the second part of it, it says, oh, I found this list right here. So let's process that list. We are going to have a recursive call there. Every time it says I found a list, it's a recursive call. So it processes it, counts Bob. Level 2, remember, level 1 has 1. Level 2 has 1 now. And then we found another list. We'll process level 3. Level 3 says we count Chet and we count Kat. So there's 2 people in that list. And then level 2 now is 3 total, because we send those 2 when we close that recursive call at the end of that list. We send 2 more back up to level 2. So we take the 2 from level 3 and we add them to here. Level 2 now has 3 total. Now we count Barb and Bert, and that makes it 4 or 5. And then we take those 5 from level 2 and we return them back to level 1. Level 1 now has 6 total, because level 1 had already counted Bob. And so now level 1 has 6. Now we count Alex on level 1 for 7, and then we have B and Bill at level 2. We start at 0 there, we count 1 and 2. Then we return those back to level 1. Level 1 has 9 total. And then we finally count Ann at the very end here. And level 1 now has 10. We return the plus 10 to level 0, which is the main program, and that's it. Now, here's the wild thing about this. This recursive counter can, what did I just do? Oh, there we go. I messed up something by accident. All right, so this recursive counter can process any number of lists at any level. For example, if I wanted to throw another array as a third member of this list, and I say Dave and let's say Dirk. Okay, so now it has 4 levels. I run that, and it has no problem finding those. So there's where it's counting Dave and Dirk on level 4. It returns those 2 to level 3, and it just does what it's supposed to. And so I can throw any level of complexity, as long as it's as nested lists. I can throw any size at this, and it will not have a problem with it. So this is a very elegant solution. Now, could I count the number of items in these lists without recursion? Yes, but with one caveat. If I don't know how many levels deep that list is before I run it, it's going to take some really crazy coding to make that work. There's no really simple, elegant way other than recursion to do something like that. So tree traversal is one of the places where we can definitively say that recursion is the best way to do something. So let's take a look at